Hello and welcome to this lecture. So in this lecture, we're going to close out a study of the initial study of the inner product spaces and inner product and dot product in particular for R2 and C2 by looking at a least squares fit. In particular, we'll focus on the orthogonality principle. Okay, so it's a very important principle in least squares. We'll see how it works here. Okay, so you remember our motivation long ago when we started this topic. We said for problems like this, when you want to fit a straight line through a bunch of points, inner product plays a key role. This because this notion of distance between point and a line is defined very nicely or captured conveniently through this orthogonality principle. So let's see what that is. Okay, so here is a line. Okay, so I picked a line through the origin because this is a subspace and it's sort of easier for us to think of. Even if it is not on the origin, we'll generalize it a little bit later. So S is a subspace, the span of U. Okay, U is my point on the thing, and the span of U is the entire line, and V is a point outside of this line. The question I'm asking is, how far is V from S? Okay, so if you want to answer this question, you can think about it in various ways. You can think about it geometrically. I'll come to that a little bit. But really, what I want to know is when I say a distance of V from S, which I can denote as d of V comma S, this d of V comma S is going to be minimum over all W in S, the distance between V and W. Okay, so you sweep through all the W in S, and for every W in this line, you calculate the distance. Okay, you know between 2 points, I know the distance, right? Norm V minus W, right? You find all those distances. There will be one W for which the distance is the least. That I am going to take as the distance of the point from the entire line. Okay, so it's a very natural, nice definition, and this is the definition we'll use for the distance. Okay, so there are two steps here. You find the point in the line which is closest to V, and you find the distance from that. Okay, that is the definition of this distance between a point and a subspace. Okay, point or any set also for that matter. Okay, so this W star was the first problem. Finding point closest to V is actually an this notation arg min. Arg is basically argument. Okay, you minimize over W in S, norm V minus W. This W is your argument of the minimization. If I say argument, right, the best possible W that you got, the one that is closest, that minimize this, that W is put out as W star. Okay, so if I say minimum over W in S, norm V minus W, this is the least distance, right? The W that achieves this minimum is arg min. So this is the notation of arg min. If you have not seen it before, okay, keep that in mind. I do a minimization over a variable. The function I'm minimizing is this. The variable that results in the minimization is the arg of that, and that I'm saying is W star. Okay, to be a little bit more clear, once you find this W star, d of V comma S is, you don't need any minimization any further. It's just the norm of V minus W star. Okay, so pictorially we can represent it like this. There is this W star which is the point on the line which is closest to V, and we know that this is basically dropping a perpendicular to the line, right? From V you drop a perpendicular, this is a geometric point, and then where you get the intersection, the W star is going to be the least guy. We know this from some geometry. We'll prove it from a linear algebra point of view, and that is the orthogonality principle, the perpendicular line that you have there. Okay, so I hope you see this arg min notation. It's a useful notation to get your hand around. Okay, so this is distance of a point from a line. So how do you compute this things? How do you find the W star? How do you find the distance? Is there an easy formula, right? So we'll do all that in this lecture. Okay. So yeah, so basically W star is CV, CU for some C. The question is, what is this C? Okay, can we find out this C? So here is an answer, an explicit answer. Let's say S is span of U cap, okay, which is a subset of C now. I mean, I give you the intuition in R2, now we're moving to C2. This is a subspace, and this norm of U cap is 1. Okay, so its U cap is normalized. Okay, this normalization is sort of important in this property. So I have a subspace which is just one dimensional, it's spanned by one vector, and that I have normalized also. If I take any point in C2, the point in this subspace is closest to this V, which is basically W star, which is arg min W in S, norm W minus V or V minus W. This is given by W star equals, I know it is some C times U cap. What is the C? It is V dot product with U cap. Okay. So you take your V and you take a dot product with this U cap through which you define the S. That gives you the thing you have to multiply U cap by to get the closest point here. Okay. So this is a very nice interesting property. The crucial property here is, if I define a W star like this, okay, so it turns out, okay, so first of all, we are going to prove this result. This is the result I am stating. We are going to prove it. And for proving this result, we need two important properties. The first property you need is, if I define W star to be like this, V dot U cap multiplying U cap. Remember, V dot U cap is a scalar, right? So this scalar multiplies U cap to give you a vector in the subspace, isn't it? The subspace is span of U cap. If I multiply U cap by any scalar, I get something in the subspace. So, but what scalar should I multiply by? It will be the inner product V dot U cap, okay. So, why is this crucial? Because if you pick this as your W star, then V minus W star is perpendicular to U cap, okay. The proof is really very simple. You take V minus W star, which is V dot U cap, dot it with U cap, and then you use the distributive property. It's V dot U cap minus V dot U cap times U dot U cap. Now, what is U dot U cap? That is 1. So, here you get a cancellation and you get 0, okay. So, the special choice of the dot product is critical because it makes V minus W star perpendicular to U cap, okay. So, this is one property. Another property you need is Pythagoras theorem. Pythagoras theorem tells you something in the right angle triangle and all, right. The version of the Pythagoras theorem in inner product spaces is this. Norm U minus V squared is norm U squared plus norm V squared minus U dot V minus V dot U. This is actually a very easy thing to prove. Let me prove that for you. What is norm U minus V squared? It's U minus V dot U minus V, okay. So, now I know all sorts of linearity that will happen here. So, it will be the same as U dot U minus V minus V dot U minus V, and this is just addition subtraction. So, you can just take it in, there is no conjugation, it is all only real values. So, you get U dot U minus U dot V minus V dot U plus, right, minus into minus will become plus V dot V. What is U dot U? It is norm U squared, this one, and this one is norm V squared, and then you have minus U dot V minus V dot U. So, these two actually are conjugates of each other. So, there is a version of this result you might have seen. So, if U dot V, V dot U is U dot V bar, and then you will have U dot V plus U dot V bar is 2 times real part of U dot V. So, this is also written as norm U squared plus norm V squared minus 2 times real part of U dot V. Okay, this is an identity which you might want to remember. A very simple modification will show you that this is also true. U plus V squared is norm U plus V squared plus 2 times real part of U dot V. Okay, so you might want to remember these things, but this is our interesting result here. Okay, so this is Pythagoras theorem. So, now what is well, this is a general version of the Pythagoras theorem. Now, Pythagoras theorem basically, if U and V are perpendicular, you get this U dot V and V dot U will go to 0. So, your norm U minus V squared is norm U squared plus norm V squared, okay. So, this is like the hypotenuse U minus V, and then the square of that is norm U squared plus norm V squared. So, this is why it is called Pythagoras theorem, okay. So, how do you use these two to show that this W star is the closest point to V, okay? How do you show that, right? So, here is the proof. Distance of V from a point CU cap in the subspace, yes, right, span of U cap is actually norm of V minus CU cap, we know this. Now, I am going to do something here without changing anything, okay. How do you do something without changing anything? This is what you do, okay. You take a this W star, let us say is C star into U cap, and where the C star is V dot U cap, right. So, this is our C star, okay. I am going to change this distance here without really changing anything. What do? Basically, I take this V minus CU cap, I subtract W star from it, and then I add it back again, okay. So, I subtract W star, then I add it back again, I get C star U cap minus CU cap. Now, I use this general Pythagoras theorem idea, I can use it quite nicely, and then this will become norm V minus W star squared plus this guy, okay. What is this guy? C star minus C U cap squared. What happened to the dot products U dot V, V dot U, those terms? Because V minus W star is perpendicular to U cap, the dot product will not show up, okay. The Pythagoras theorem will apply and you will get just this plus this. Now remember, norm square is positive, right? Okay, so this norm square is positive. So because of that, this becomes greater than or equal to V minus W star square. So if you take any point C U cap on S, its distance from V is greater than or equal to the distance of V from W star. So clearly W star is the one which gives the closest, which is closest to V, or gives you the least distance when you see from V. Okay. So this formula is important to sort of remember. W star is V dot U cap U cap. So if you're looking at a span one dimensional subspace, you have another point, the projection or when the perpendicular down to it is given by this dot product. Okay. This is also called projection. I haven't really formally named it, but this is what it is. Okay. So here is a sort of a generalization of it. So here we had only like a straight line going through the origin, right? So what if you don't have a straight line through the origin in R2? What if you have y equals ax plus b and I have a v which is x naught, y naught, okay? And what is the distance between here and here? I know I have to draw the perpendicular, but how do you use the orthogonality principle? So here is the definition as such. I want to find a w star such that, you know, this guy is closest. That's what I want to find. Okay, but I know w star is on this line y equals ax plus b. So it will be x star comma y star, and this y star will be ax star plus b. Okay. So now let me take another point u, a convenient point u, which is 0 comma b on this same line. Okay, on the same line I have y equals ax plus b. So I take another point here which is conveniently taken as 0 comma b. I know 0 comma b passes through this point. Now my orthogonality principle tells me v minus w star has to be perpendicular to w star minus u. Okay. I can take any other u also. I was just for convenience I have taken 0b. You can take any other point also. You can take 1 comma a plus b. You can take whatever you want, but you will get the same answer, by the way. Don't worry about it. So you got 0 comma b here and then w star minus u. So these two have to be orthogonal. Okay. Now if you simplify this, okay, you put v equals x naught, y naught, put w star equals x star, ax star plus b, and then put u equals 0 comma b. You simplify, you will get this dot product to be this expression. Okay, x naught minus x star times x star plus y naught minus ax star minus b times ax star equals 0. Now from here you can solve for x star. This x star will cancel. You will get another x star here, and then you can back substitute it here to get y star. So just with this orthogonality principle, you get a very clear and full expression in terms of a, b, x naught, y naught for x star and y star. What is even nicer is there is a very simple expression for d star. Okay, d star is just x naught minus x, the distance between u and v and w, right? So you subtract x star minus x naught squared plus y naught minus y naught, y star minus y naught square. That is d star square. So d star square has a very simple and evocative formula, right? What do you do here? See, y equals ax plus b, right? So y minus ax minus b, right, is equal to 0 is sort of the equation of the line, y minus ax minus b. In that equation of the line, you put y naught x naught. So you get y naught minus ax naught minus b whole squared divided by 1 plus a squared. So why do you do 1 plus a squared? Okay, that you have to do. Okay. So when you do that, you get the square of the distance. So it's a nice little formula. So this operation, by the way, is called projection. You're projecting this point on the line and you get this point w star, and this projection will always have the spring being perpendicular to the line. Okay. So this is a nice formula to remember for distance of a point from a straight line, and you see how linear algebra and the dot product in particular is very useful in this simple calculation. Okay, so here are some examples. I'm not going to go talk about it in great detail, but you know, the dot product basically is if you have a vector v and if you have a unit vector u cap. This is called a unit vector because it's got length 1, right? So when you do v dot u cap and then multiply by u cap, you get this w star, which is sort of like the component of v along u. Okay, so you can think of this as like a projection that's happening here. It's a component of v along u. Okay, that's the way you think of it. This is a simple straightforward formula. I've given you the formula here. You substitute, you will get all these answers. So let me close with this little reference back to this least squares fit, which is with the perpendicular offset, as this is called. Okay, so you have these n points x1, y1 to xn, yn, and you want to fit a straight line y equals ax plus b here, right? My distance from xi, yi, perpendicular distance di, I can calculate, right? Yi minus axi minus b whole square by 1 plus a square. And then you minimize over ab this summation I equals 1 to n di squared, which is this complicated looking formula, summation I equals 1 to n yi minus axi minus b whole squared by 1 plus a squared. Okay. So, you see how once you know the distance from a point to the straight line, you can easily plug it in and solve for this AB. So, how do you solve for this AB? How do you do this minimization of two variables and all that? For this you need some multivariable calculus, which you may see somewhere. It is not part of this course. So, we are not going to go through the formula for how to find AB from here, but this is the general principle. Okay. So, that concludes this lecture and discussion on the least squares fit. But by the way, perpendicular offset is not the only offset you can use. You can also use vertical offset. If you use vertical offset, then your error is just yi minus axi minus b. So, this denominator will not come. So, it will just be summation I equals 1 to n yi minus axi minus b whole squared without this denominator, and that is called vertical offset. So, this is perpendicular offset. This is one way of doing least squares fit. Okay. I hope this was interesting to you. Hope you got a sense of how inner product enters the picture, how it helps in the definition of the adjoint and all of that. So, these are very important and have a lot of very good practical applications. Thank you very much.